All right. Okay. So I'm just gonna pick up where we are because we only have like 30 seconds. But like it turns out importance weighting is just being used blindly in a context where the underlying motivation for it didn't exist. Or like, and it turns out that like we're able to show that um, what, if anything, the effect of importance weighting is on the learned model when you're actually in the deep learning setting training over parameterized models to the point that they shatter the training set depends in a sort of completely intuitionless sense on the number of training epochs that you've trained and the kind of regularization that you use. But these are like the wrong knobs to be turning. These are not distribution matching knobs. These are capacity control knobs. And so that was, sort of, another example of, I think, a negative result. I'll give another result I think matters a lot to the, I see that people doing this stuff in NLP, so it's really important. Is a lot of people have sort of are so confused about domain adaptation. So basically domain adaptation is a setting. I have data from one distribution that's labeled and another distribution is unlabeled. And the idea is I want to make a model that predicts well on the unlabeled, on the target distribution from which I only have unlabeled data. What can I do? So some people basically have this sort of, it seems intuitive. It's a cute idea, cute story, which is the way that I'll predict well on the target domain is to make the target and source data look the same in latent space. So I'll basically map them into the same latent space, apply a discriminator loss on top, and then apply a classification loss, but only for the source examples. So, and this is motivated by saying, hey, there's a theorem from Shai Ben David in, 20 years ago or 10 years ago that says that the target domain is bounded by the sum of the error in the source domain and the divergence of the source and target data, and some term that is complicated, so let's ignore it. And it turns out that that third term really matters. The third term is an irreducible lower bound on your target error. The theorem does not say that doing domain adversarial stuff makes sense, but somehow this has gained such currency that people are publishing thousands and thousands of papers doing domain adaptation with these domain adversarial networks. Sometimes it works, sometimes it doesn't. The dirty trick is it's also extremely unstable. So it turns out that the results reported in papers are extremely misleading because they almost always are only reporting the result on the time that it worked. And the way they know which time it worked is because they actually are looking at labeled data from the target domain. So here it's a negative result in terms of this maybe a more malignant kind of the evaluation is fundamentally wrong in these papers. It's a negative result in a mathematical kind that a theorem is fundamentally misstated and misinterpreted. And it's also one for which it takes about 5 minutes of effort, I think, to at least see the broad strokes of why. And so I think the biggest danger is that you have thousands of people writing papers just kind of rushing to use something and propose something and get a paper accepted, but without thinking of does this actually make sense? And it turns out that all you need is basically, if my source and target domains have different class distributions, this is sort of guaranteed to fail. And that even when it doesn't, it's certainly not guaranteed to succeed. It's an underspecified problem, but we, at least by being clear, can already articulate, okay, this is a failure mode. This doesn't in general work. And so we have a weird situation now. We have a whole literature that is so convinced that has been so sort of confused that they actually don't even know the difference between the domain adversarial methods and the problem. They actually, you ask people what is domain adaptation, you'll see a lot of papers say domain adaptation is when you change a discriminator to do blah, 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 blah. So they don't even know the difference between this one proposed family of approaches and the underlying problem. And the proposed family of approaches doesn't actually solve the problem, or at least not in their current form. That's another negative result that we had. And finally, the last thing that I'll mention is that we have a lot of stories about pre-training, and the stories that people tell are mostly about knowledge transfer. And these stories have incredible currency, this is the whole thing, the models, both in the sense of their driving research, that the intuitions people have are all about knowledge transfer, but also even in the sense that concerns people have about the models, oh, we're training these models on enormous corpora of unknown provenance, whatever. What if those things are creeping into the model? And the question is do we even have any understanding of what's going on in pre-training? And Here's one example. And so this is not necessarily bearing on like BERT and Electra. This is specifically focused on the summarization setting, but here's a weird finding that we had. It turns out that you could look at, say, what is the performance of a pre-trained T5 model? And they get these great numbers on the top line on the right. What's the performance of a randomly initialized T5 model? And they get these terrible numbers. And I say, okay, let's design a pre-training task that has no real data, no knowledge at all, and a fake task, like some procedurally like assigned task, like, copy out a sentence, any sentence that contains a particular keyword, just copy that sentence, something like that. And we designed a bunch of like fake tasks like this, all using no data. There's no knowledge. When I say no knowledge, I mean there's no empirical, there's no collection, there's no observation of the real world. All that we've done is write, 10 lines of code that generate a synthetic data set. That's all the knowledge that is there. It's not like we've got, billions of data points. So the point is that we have something of like an analytic form, not of like an empirical form. And say, well, if we train on these nonsense passages, not a single real word, there's not even real vocabulary there. And there's not a real vocabulary. There's not examples of answers from a real task. It's not even isomorphic to the real task. And we do pre-training here. It turns out we recover across many tasks almost all of the benefit of pre-training, and in others, just like a startling amount of it. So there's some story about transformers are fundamentally unstable in a way that there may be a benefit that has something to do with knowledge transfer of some kind, or that story might pan out for some of these models in some places, but we just sort of, it's a thing that we parrot all the time as though like we know it's true, or it's like a substantiated scientific theory whenever we're doing pre-training. And it seems like in a lot of the instances where we're doing pre-training, there is something else going on, and it has probably a lot more to do with optimization than it does to do with knowledge transfer. And so, you can check out this paper. It was just published in Findings at the CMNLP. This is with my student Kundan Krishna. It's basically, does pre-training actually require knowledge transfer? And so, I'll end there. I know I'm way over time. And thanks everyone. And I think we made it despite the technical difficulties. So I hope there's yeah. I'll turn over the mic. Yeah, I don't know if I don't know if you're moving on to the next talk and I should be answering questions in the chat, or if I say the answers out loud. Okay, so one question is, how do I see the construction of new data sets as a way to mitigate some of the issues? So I think that broadly, I think data set creation, I want to be clear that I think it's a valuable like mode of contribution, that there's a lot of context in which a new data set is extremely, I don't think that it's like, but I want to be clear that like, I don't think it's sort of, how do I put it? It's like, it's almost like to what extent do you see math as a solution? And it's like math is a language for expressing solutions, but it's not like just like, do math is like itself a solution. So I think the question is, you know, you know, like I think, for example, that there are some, like, data set creation can be a way of solving problems if you create the right data set that resolves, whatever issues in the previous data sets. It's like that, but it could also be a way of introducing problems. I think we saw that in the case of a lot of the reading comprehension benchmarks that were created a bit hastily, but where people were, in the form of presenting this contribution, creating a benchmark that maybe wasn't, people were using it in a way it wasn't actually maybe like measuring what people thought they were measuring. So I think data set creation is like, it is like one of our, it's like we have a handful of things that we could do. Like we can go out and collect data in the world. We can build common resources and benchmarks. We could develop statistical methodology. We can, engage in kind of like some serious, like, kind of normative kind of reasoning and conversations, and develop some frameworks. Like there's many ways that we make progress as a researcher, but I think in any of those pursuits, we're sort of capable of falling into these traps of, presenting misleading results, doing work, like maybe falling victim to the wrong set of incentives, creating problems as much as resolving them. And so I think this research is also saying that if you make maps into shared representation space invertible, and the problem goes away. That's not true. This is like I can say just like broadly, like the problem is like here, I'll give you an example of how it's obviously not true. So when I say not true, I don't mean that like the paper that said it is necessarily wrong. It's possible that they were like a really rigorous paper that made a very strong set of assumptions under which it is true. It's also possible that like someone just said, oh, let me just like enforce invertibility by like, having all my weight matrices have like be like non-singular, and all my activation functions invertible, and keeping the same dimensionality between input and hidden representation, and do some experiments and find, does the problem seem to go away in my experiments? And I think the danger here is that there's a lot of this stuff that's like, how do you put it? Like theory is very bad at telling us what, like, how do I put it? It's like usually trailing and like telling us what's going to work, but it's like very good at telling us what's sort of like obviously wrong. You know what I mean? And things that are obviously wrong don't like magically become, you know what I mean? Like, right. Like, for example, it's like I'll give you an example of this kind of thing. Someone says, there's lots of results out there that say that label smoothing causes models to be better calibrated. Right? I'm imagining many people in this room have heard some form of that claim somewhere. And that's obviously wrong, right? It's just flat out wrong. And it's so obviously wrong that all you have to do is like construct a simple example. The counter example is, let me just have a data set that consists of two examples. One is always positive and one is always negative. And like if I do label smoothing, what happens? Okay, now I'm trying to, for the positive example, I'm trying to hit 0.9. And for the negative example, I'm trying to hit 0.1 instead of trying to hit 1 and trying to hit 0. So is that model calibrated? When I say one example, I mean like, you can imagine that like there's only one unique value, two unique values that the input could take. So, imagine you can see them many times. It's not just that like this is actually a generalizable, that, I'm describing the distribution, not a finite sample. Not just saying you have two examples, I'm saying this is actually the distribution. There's just two atoms, two inputs. One is always 1, one is always 0. What happens if I do label smoothing? It just makes the model less confident. It doesn't make it, but in this case, being maximally confident would be calibrated, because the model's always right when it predicts on class 1 and on x1, and it's always right when it predicts on x2. For the model to be calibrated, it has to have confidence 1 and confidence 0, or confidence, arbitrarily close to 1, arbitrarily close to 0, to get, for some, reasonable like measure of calibration, more calibrated. So it's like obvious that like if you just look at it, you're sort of like, okay, what's this actually doing? What this is actually doing is just making the model, like in a very blunt core sense, sort of somehow less confident. Now, obviously, you could do an experiment and take a model that's badly overfit and add label smoothing, and you'll find that like, okay, the model's badly overfit, so the confidence scores are always overstated on holdout data. And if I do the label smoothing during training, I've made the model just like in a blunt way, just report lower confidences across the board. And so it's going to appear to be better calibrated in that I'm going to get a better measure, like I'm going to get a better score on my calibration metric. But you have to understand, like I think when we leap past, like where people have gotten lazy, I think, is that we're always relying on the fact that like we're playing an architecture space, we're playing an inductive bias space, but like we've assumed like we're working with the same handful of like reasonable loss functions that actually are coherent and make sense. Like if you actually optimize cross entropy loss or something, you're sort of doing the right thing in the limit. But now you're doing something that's the wrong thing, even in the limit. You know what I mean? And this is where I get to like things don't magically, like things that are the wrong, like obviously the wrong thing to do, even in the simplest counterexample, like even in the simplest example, forget even counterexamples, just like any arbitrary example, it's going to give you, it's not going to calibrate the classifier. It's going to give you, it's going to be wrong. Things that are wrong, they don't magically become right when you have finite samples or when you have high dimensional data. They might happen to work on the data sets that you evaluated it on, but it's not the same thing. And so, in the case of like the shared representation thing, like, no, obviously it's not true if they're invertible, because all you have to do is say, let me just have two domains where the supports are disjoint. So X is, like I have my source domain is like, one region of the sample space and has no overlap with the other one. Now, maybe they're like, like things like when you use data sets like MNIST and MNIST-M, there's no actual overlap in the supports. One of them is handwritten digits that are black and white, and one of them are like Technicolor or something like this. So you could have an invertible mapping that gives you an arbitrarily incorrect alignment. There's no reason why invertibility has to entail. So like it's possible that someone did is they sort of said this was their intuition. They told the story, then they came up with some method that makes the model like approximately invertible. And then they did an experiment and they said, okay, see, like it did better on my one experiment. But that's not, like the same as saying that like it actually, the problem goes away. That's saying like, hey, one guy got one favorable result. So I haven't read the paper, so I can't comment specifically, but, in general, it absent like some, like unless you give me like a long menu of like assumptions under which this then suddenly magically becomes true, it's like in full generality, it's definitely wrong. Adam says a minute ago, a lot of these issues have to do with the structural incentives of our current academic and general research environment. How can you say something about how PhD students can operate in relation to these incentives? So, it's a good point. Incentives have a lot to do with it. And so I guess will be the final question. But I mean, it's one of these things of like, I don't know. It's it's one of those things of like if you go around like counting $100 bills in Central Park, and you get at midnight and you get robbed, it's like there's a problem with crime. But there's also a problem with like you being an idiot or something. And like, okay, we need to solve both those problems. Nobody's exonerated. Like the criminal still shouldn't have robbed you, but you, like what the fuck are you doing? Forgive my French, right? I think there's a similar culture with PhD students. And I think that we need to think about that, like, okay, there are structural incentives, but at the same time, I think we need to have like a bit more. I think this, we should deal with the structural things, but I think we also need to talk to our own students and be like, you're an adult. Like this stuff that people are doing in a lot of papers. So some of these things are like, hey, research is hard. You have to know how to engineer. You have to know something about language. You have to know something about stats. It's hard to get it all right. But some of the stuff that we're seeing is just flagrantly wrong. And, I think like one side of this is like, we need to set a culture to people. It's like, I don't care what, it doesn't matter. Like there's an incentive to steal stuff because then you'll have more money. You don't go out and steal stuff. But the same thing, it's like, you don't not show a result because it makes your model look weak. You don't say, I'm not going to run this test because I'm afraid of what I'm going to see. I think there is like a sort of culture of accountability that we need to create. The other thing I'd say is that, on one hand, the incentives, there's a lot of incentives here, but they're mostly like positive incentives. When I say positive, I mean that like, if I look at my like colleagues who are like in philosophy or in some field that's less overheated and doesn't have millions of dollars being thrown at them, it's like, the worst case scenario faced by a PhD student for doing like honest work versus good work or something is, to the extent that like, they're sometimes in a situation where they're like deliberately doing something wrong or like really going down the wrong path, like the extent that like, incentives are manipulating that, like, their floor is so much more secure in our field than just about any other field. So I think we really need to like kind of look at ourselves a bit more critically and be like, it's not like, oh, like you're out on the street. Like we're in a field where someone who's published like even a little bit gets a really high paying job in industry and has way wider academic prospects than, it's not like the, like Hunger Games situation that like if you're a philosopher. And so I think we do need to be like, okay, we need to toughen up a little bit. I think another aspect of it is that some of the incentives are already there, but students don't see it. Right. So there's an incentive, like it makes a big difference. Like I think there's like the real prize to me. It's like, it's not getting a paper in EMNLP. It's not getting a paper in ACE. It's not getting a paper in NeurIPS. It's not getting 2. It's not getting 10. It's, it's sort of like, okay, like look at your future. Where do you really want to be in 10 years, 15 years? Do people actually read your papers, or do you just have a pile of them? And do you have the respect of the people whose respect you would actually want? Like, I think for me, the thing that like really, 2 things made me dial that all into focus. One was that I had the experience of people actually reading what I was writing and giving like critical responses before I was publishing papers, because I kind of developed maybe more presence as like a expositor, like in a blogger before, like in the early years of PhD when I was just figuring out what research was. And so I had a little bit more direct connection to the like, oh, like just getting it, just putting something out there wasn't necessarily that good because it could be really embarrassing if I got something badly wrong. And I was like, I'm kind of exposed. Like I had a student once had a paper out there and it blew up a little bit on Twitter. And I sat him down, I was like, how does it feel? And he's like, it's exciting, but he's like, but I'm also nervous because I'm like frantically triple checking my code because I'm just so terrified that it'll turn out I made one mistake and people are going to find it. And so I think a lot of these incentives, are partly because students aren't seeing like, that what are people looking for when you're, at the level, even at the level of hiring faculty. I think there's a huge miscalibration between what students see as like the myopic incentives in there in terms of get out a paper or whatever versus, like I think, and maybe this is a bias of the pool that we have. I think we have lots of candidates who have 3 times as many papers that are not considered nearly as strong as someone who's published less, but everyone knows they're really an authority. And so I think like it's your responsibility as an advisor, I think, to push those incentives down to the people to provide them the benefit of your experience. I mean, I think for those of us who are a little bit further down the path.
All right, Zach, I'm sorry to interrupt you.
No, we're way over.
Yeah.
Cool.